Hello everyone. In this second lecture, we are going to discuss about the principle of flow in pipes and also the concept of head loss. So why does takes place inside a pipe? The common idea is that flow takes place from high pressure to low pressure region. So that's what we have demonstrated in this figure. That means in this first tank, water has higher pressure because of greater depth of water, and here the pressure is less, and therefore water will flow from high pressure to the low pressure tank. But that's not always this simple, and therefore we need to have a better idea of what actually governs flow of water or any fluid. Sometimes, for example, in this figure, this tank has obviously higher pressure than this tank because the depth of water or fluid is more here. But still, because this tank is at a very high elevation, water will flow from this tank to this tank, although the pressure at this point is more. In this case, therefore, elevation difference has overcome the pressure difference. The pressure difference is trying to push it this way, but the elevation difference is trying to push it this way. And since the elevation difference is bigger, so it can push it in this direction. Let's take another example where this tank is at a higher elevation than base of this tank, and in this case we can increase the pressure by adding even more water in this tank, so that although there is an elevation difference, the pressure is so high that it will push water in this direction. So here pressure difference has overcome the elevation difference. Sometimes we need to increase the pressure artificially because we cannot keep adding water indefinitely in this tank because the tank will have some limitations. So what we can do is we can increase the pressure artificially. For example, in a hypothetical case, if we add a piston like this, and on top of that we have put some kind of load, so this load has put this additional pressure, and because of this additional pressure water is flowing into this tank. This is done in most of the pumps where we need to raise water from a lower elevation point to a higher elevation point, and we do that by artificially increasing the pressure at the low elevation point so that water is pushed upwards. It's not always by means of a piston, there are some other ways as well, but the basic idea is that we increase the pressure at the lower elevation point and therefore flow takes place in the upward direction. When we come to open channel flow, the flow is generally driven by the component of gravity. So for example, in this channel, this is the channel bed, and if you take two sections here and here, both these sections have equal depth and therefore they will both have equal pressure. Suppose P1 and P2, but both P1 and P2 are actually equal, so there is no pressure difference to carry the flow, but water is carried by the small elevation difference between these 2 points, because this point is slightly above this point because of the slope of the channel. So therefore whatever was the weight of water in between these two sections, so that weight of water will act downward, but it will have very small component in this direction, which is not exactly horizontal but along the slope of the channel, and because of this small component of the weight, water will keep moving in this direction. This doesn't mean that pressure difference doesn't have an impact on open channel flow. If you encounter a situation where the flow depth is more in the downstream direction, that means here, and flow depth is less here, in that case here the pressure will be more and here the pressure will be less. Therefore, in this case, the pressure difference is actually giving us a net force which is acting against the flow. And what will happen then is, although the elevation difference or the slope of the channel is trying to move the water in this direction, because of this pressure difference in the opposite direction, water will be pushed back and therefore the velocity will reduce as it moves down the slope. And we can see that because velocity is reduced, that means some retardation is going on, also the depth also increases. Now let's take another example. So this is, suppose, a jet of water that we are targeting at a bucket or a pool. So what happens is that as soon as this this jet of water strikes or hits the surface of water in the pool or bucket, then from this point up to this point, if you measure the head, the pressure head, then pressure will increase from here to here towards the in the downward direction, but the datum head decreases. That means the piezometric head, which is the summation of datum and pressure head, that is Z plus P by rho Z, it remains constant all throughout this stationary liquid. And therefore, because there is no difference, that's why it is stationary, there is no flow. But this jet will still flow into this tank and cause some disturbance. How can it do that? Inside this tank, there is no pressure difference, there is no head difference between different points, and therefore it should not flow. But because this jet already had some velocity, that means already had some kinetic energy, and because of that kinetic energy, it can still flow, although the combined effect of elevation and pressure is not causing any flow. It is only driven by the initial velocity it was given. Similarly, when we shoot a jet up into the air in the vertical direction, then inside the pipe, the flow was driven by the pressure difference or head difference. But as soon as it gets released from the pipe through the nozzle, suppose, then it only has the kinetic energy to keep it going, and the kinetic energy can only keep it going up to some level which is equivalent to the velocity head. That means if we convert this kinetic energy at this point to potential energy, then that will be equivalent to this much height of a column of water. So therefore water will rise up to this level and then it will fall back like a fountain. So what do these examples tell us? That means flow is governed by or driven by pressure difference, elevation difference, and also initial velocity or kinetic energy. Now these three terms may look familiar because we have already learned that in Bernoulli's equation we found there were three heads or three kinds of energy, that is pressure head, elevation head or datum head, and velocity head or kinetic head. In addition to these three kinds of energy or heads, we have another thing which is always there in flow, that is the resistance to flow. And the resistance to flow is given by either viscosity, which is the friction between individual particles of fluid, then friction with the solid boundary. If it's flowing inside a pipe, then with the solid boundary of the pipe there will be some friction, additional friction, and the turbulence, that is the randomness when flow doesn't go in a straight line but goes forming some eddies. So in that case also that causes some kind of resistance. So because of this resistance, either viscosity or friction or turbulence, some amount of energy must be spent to overcome this friction, and that is what we call as head loss. So whatever pressure, suppose this is a pipe. At this point it has some pressure P1, and it is flowing with a velocity V, suppose, and at this point it had pressure P2. The pressure head at this point, which is P1 by rho g, will decrease to P2 by rho g, because whatever is the difference, that is the energy being spent in overcoming the frictional resistance, which is always acting against the flow. So every unit length, as the flow takes place, some energy will be lost. How is it lost? It is lost in the form of heat or vibration or sound, and that's what we call the head loss. Now, the head loss in flow is governed by these factors generally. That is the roughness of the solid boundary. That means when, let's say, a pipe, when flow takes place inside the pipe, if the pipe is very smooth, then the flow will also pass very easily. But if the pipe boundary is very rough, in that case flow will not be able to pass smoothly, and it will cause lots of this kind of turbulence, and a significant amount of the energy that the flow had will be spent in overcoming this kind of disturbances. So the flow will not be able to pass with a very high velocity, and therefore that means the energy is lost in overcoming the roughness induced friction. Then viscosity is quite obvious, because if it's a very viscous fluid, there will be more resistance between the flow particles themselves, and any kind of relative motion will be resisted, and therefore more energy will be spent in overcoming that resistance. Flow characteristic dimension, that is the third term. In case of pipe, it generally means diameter. In case of a channel flow, suppose water is flowing inside this kind of a channel, in that case generally the depth gives us some idea of the characteristic dimension. The characteristic dimension in this case means the dimension of the flow, which gives us some idea about how much will be the resistance. So in case of a pipe, if the diameter is a certain amount, then it will cause some kind of resistance. But if the diameter is very large in a pipe, then most of the flow will be away from the boundary, so the boundary friction will not be affecting most of the flow. So that's how the characteristic dimension, which is the diameter in case of a pipe, and depth or width or some representative of both depth and width in case of a channel. If it's a rectangular pipe, then we'll have to figure out something else, which may be either this dimension or some representative dimension of both of them, which will give us some idea about how much the solid boundary is affecting the flow inside the pipe. And therefore we can say that in case of a circular pipe, the diameter d is the dimension that's affecting the flow or affecting the head loss. If the diameter is small, more head will be lost, because most of the flow will be affected by the skin friction. If it's a large diameter, then less head will be lost because of this, because most of the flow is away from the solid boundary or the circumference of the pipe. Then distance of flow or length of flow. In this case, if you consider a long pipe, then from this point to this point, more head will be lost. However, from this point to a nearer point, small amount of head will be lost. So that's how it's affecting the head loss. And finally, velocity. In case of velocity, we say that more head loss causes more velocity, or more velocity causes more head loss. In case of these first four terms, it was quite obvious that more roughness causes more head loss, more viscosity causes more head loss, more less diameter causes more head loss, then greater distance causes more head loss. But in case of velocity, it may seem sometimes confusing. Does velocity cause head loss, or head loss causes velocity? So a greater head loss causes higher velocity. Head loss means head difference, but we'll discuss why that head difference is also termed as head lost. And higher velocity leads to higher head loss. So we'll examine these two statements now. Let's take these two tanks or reservoirs, A and B. Water in tank A used to be at a higher elevation or head, that is here. But after moving to tank B, now it has only this much elevation, which means that this much of head is being lost. But what do we mean by getting lost? When water flows from here to here, because of this head difference, it will govern the velocity of flow. If the head difference is more, then the velocity will also be more, and therefore water will enter this tank at a higher velocity. But where is the loss then? You see, when water enters this tank, this velocity that with which it enters, let's say it is v, it can also be converted to again the head, that is v square by 2g. But in these kind of situations, we can never get that head back, and it's actually lost into the surroundings because as soon as it enters, there will be lots of turbulence inside this tank. There will be waves and bubbles and eddies. Some evaporation will also take place, and that's how we can never get this head back. If it was a very small tank, we'll explore that part later, then we could get that back. But in this kind of a wide tank, that velocity head will simply be lost. And actually you can see this loss happening physically, because if you observe the tank for a certain duration, you'll see that this water is moving inside the tank, some bubbles are forming, and that will keep on going for a few minutes or several minutes, and after some time the water will become still. So that the disturbance or the turbulence that was caused because of the velocity will slowly die down, and that energy will be dissipated into the surroundings by means of heat, vibration, or sound, and this small amount of evaporation. So that's why we call that the velocity, the head is actually lost when we have a high velocity. Now, can we have a smaller head loss? We can if we let water flow under a smaller head difference. That means only this much. Here water had this much head, now it has a smaller head, but not too small. It's only smaller by this much amount, unlike the previous case where the head loss was more and the head available at the end was less. Now in this case also, since the pressure difference or the head difference is small, the velocity will also be small. So the velocity with which it will enter this tank will be small, and therefore there will be less turbulence, less waves, less bubbles, and therefore the loss of energy will also be less. Now imagine a situation where we have almost no loss. So instead of a large tank B, if we use a very narrow tank B, then what will happen is water will very soon fill up this tank and water will reach almost this level. So what is this level? Since some amount of water has already flown out of this tank, so in this tank also water level will drop by a very small amount. And since this tank is very narrow, there is less room for random movement or turbulence, and therefore the loss of energy or head will also be less. And because very soon the head difference is, suppose when the head difference is this much, the velocity will already be very less, and therefore we can say that since velocity is less, therefore head loss is also less. Now in case of a viscous liquid, this different color is used to show that it's a different liquid having a different viscosity, let's say more viscosity. So in this case also, it will enter this tank B with a smaller velocity because a significant amount of head is already lost in travel through this pipe because of viscosity, and whatever velocity it had while entering this second tank B, that will be very easily dissipated into the surroundings. And it doesn't mean that the velocity, the head loss will be less, because after some time here the level will be this much and here the level will be this much. So that means this much amount of head will be lost anyway, but the rate of head loss will be less because the velocity is less. So to see the same amount of head loss, that is this much, you'll have to wait for a long time, unlike in case of water. Now let's take another example. What if instead of carrying water from one tank to another, the pipe is open at the other end? That means water is simply allowed to flow out into the atmosphere. What will happen here is the water will fall on the floor, and on the floor it will spread out, and because of friction after some time the spread will stop. Some bubbles will be formed, some waves will be formed, but after some time everything will be stationary and steady. And that's how we know that the head, whatever velocity head it had at the outlet, that is v square by 2g, is being lost into the surroundings or to the environment. Again, if we consider something where it is flowing up, then it will flow up to almost this level, almost, because while flowing some head is already lost because of friction inside this pipe, and also with friction, due to friction with the atmosphere, so it will not exactly reach this level, maybe slightly here. So when it rises up to this level, you are still gaining back that head, which is this v square by 2g, but what will happen is it will again fall back, and by the same process of forming bubbles, waves, and friction and evaporation, that head will be lost. We can store this head if we put a bucket somewhere here. So in this bucket, water will be stored. That means you have restored this much amount of head. But this much you have already lost because you have kept the bucket at a lower elevation. If you keep the bucket right at the top of this fountain and collect the water, then you can say that I have restored whatever v square by 2g head was there at the outlet. I have now restored it in this bucket. But if you don't store the water, then the water will simply fall down on the floor and it will be lost. This concept is useful in case of water supply. Generally what happens is we have a very large tank, maybe hundreds of feet above the ground level, which supplies to the public, but each household can also have a separate small tank where you'll store water. Maybe you have water supply only for 2 or 3 hours in a day. So in that 2 or 3 hours in a day, you collect the water in this kind of a tank, which is maybe 10 or 15 feet tall instead of being 100 feet tall. So you collect the water, and that way you have restored or collected this much amount of head. This amount of head you can use later on when you're opening a tap in your kitchen or in your bathroom. So this much amount of head is useful then. If you store this water in a underground tank, then you don't have that restored head and you have to fetch water from this underground tank, either using a separate pump or using a bucket and so on. But if you store it at a higher elevation, that means although this much amount of head is lost, this remaining amount of head you have stored in your overhead tank at your house. So now we can answer that. Does head loss cause velocity, or velocity causes head loss? So the answer may be greater head difference causes water to flow with more velocity, which is obvious, but a head equal to this difference is said to be lost. It's said to be lost because that is converted to kinetic energy. Whatever was the head difference, it is converted to kinetic energy, and we are calling it to be lost only because that kinetic energy is generally not restored back or converted back into pressure or daytime energy, but it's either used for various purposes such as washing or cleaning and so on, or if you keep the tap open without using the water, then it is just lost into the surroundings. That's why we say that it is the loss of head. Now these are two losses that we have discussed: loss because of friction with the pipe boundary and loss because of this velocity, which we generally do not restore. There are some other kinds of losses as well. For example, losses in bends and curves. When the pipe is bent like this or it has a curve like this, there is the flow will have to spend some more energy in overcoming these kind of obstacles or disturbances in the flow path, and some additional turbulence, some additional friction will appear here, so some more head will be lost. These are called minor losses. Another other kinds of these losses are expansion and constriction. That means when you have a pipe of certain diameter and suddenly the diameter increases, then in this transition there will be some kind of turbulence here, and in overcoming this turbulence, some more energy will be lost. Similarly, when you decrease the diameter suddenly, then also there will be some kind of turbulence here, and again some additional head will be lost. Entry and exit, that means when water enters this pipe from a large reservoir, some energy will be lost, some small amount, so that is called loss at entry. And loss at exit, that we have already discussed while discussing the velocity head loss. Other types of losses can be in pipe fittings, that is there will be joints in pipes, there will be valves in pipes, so they will also introduce some kind of disturbance in the pipe flow, and some more head will be lost in overcoming these things. All these losses are also called minor losses, and loss due to friction in pipe is called the major loss. And that's because in most cases the pipelines are very long, and whatever energy is lost due to friction, whatever head is lost due to friction, is considerably higher than all these losses, and therefore that is called major loss, and all these losses are called minor losses. So that's about the concept of head loss. It's useful in control of flow of water. For example, if you are supplying water to various households from an overhead tank, then you have to be careful in determining the head loss in the pipes. That is, the pipes have to be of good quality, smooth surfaces, so that the friction is less. And also you need to lay out the pipe network in such a way that the distance traveled to each household is minimum possible. Otherwise the head will be very less, and more head will be lost along the length of the pipe. Sometimes at flow outlets we introduce head loss artificially. For example, this kind of attachments that we fit into our taps that you have seen, these are used so that while washing your hand you don't need a very high velocity of water, so therefore we introduce this kind of um, attachments at the outlet so that the water flows at a lower velocity, because that's enough, and therefore less water is lost and less head is lost. There is another example. It's not about pipes, but in spillways. A spillway is portion of a dam over which water is allowed to flow over the dam. The dam will be maybe 100-meter 200-meter tall, and when there is excess water because of flood, then we generally let the water flow over this. But when it falls from a 100-meter height, it will have a very high velocity at the downstream, and this high velocity is dangerous because it can also cause erosions at the downstream river, which we do not want. So what we can do is we introduce some roughness artificially so that water doesn't flow smoothly here, and most of its energy is lost in overcoming these obstacles, these roughness elements. So they introduce some additional friction, and therefore some more head is lost, and the water is slowed down, and it flows with a smaller velocity and greater depth, and therefore the downstream riverbed is secured. So I hope you have a rough idea of what head loss is and what governs pipe flow or flow in general. In this lecture we have not discussed the mathematics part, so in the next lecture we'll get into what kind of formulas are used in case of computation of head loss. We have already derived one such formula in case of laminar flow, but in most cases in civil engineering applications the flow is turbulent, so that formula is not applicable here, so we'll have to use some other formula. So we'll get into that in the next lecture. Thank you.